Okay, so let's repeat that. A couple people asked me about number 45 on the homework, and the question had an A, B, and a C part that I'd asked you to do. I think it had some other parts too, but we haven't gotten to that yet. And the A part was determine the asymptotes, vertical and horizontal asymptotes. The B part was tell me where the intervals, where the graph was increasing or decreasing. And the C part said, well, determine any relative maxes or mins. All right, so if we think back through everything we've done, how do you determine where you have a vertical or horizontal asymptote? Start with vertical. Like typically, think in the work that you've done, where do you have vertical asymptotes?
Equals 0.
When the denominator is equal 0, as long as maybe that factor didn't cancel in the numerator, which would have made it a whole, right? Well, I don't even have a rational function yet where I can factor the denominator. So I thought, the best thing might be able to just change it into a rational function by adding all this junk together. So I rewrote that as that, brought that down, common denominator, and I got to here. So from this, I can't factor the numerator. Kind of looks like I can, but I can't. And that would tell me that there's a vertical asymptote at x equals 0. And then the horizontal asymptote, remember, we look at the coefficients, which are both squared. And if they're both squared, if they're both squared, I'd look at the coefficients. And I got 1 over 1, so y equals 1. Now, technically, and I think Akram mentioned this or asked this, he said, to find the horizontal asymptotes, do I take the limits to infinity? Yes. That's what a horizontal asymptote is when you're thinking in terms of the calculus language. Because I want to know what that graph is doing towards infinity. And if it's not flattening out, it's probably going up and it doesn't have a horizontal, right? It has a slant or maybe just some other weird oblique behavior. So technically I could have taken the limit, and if I had done that, I would have gotten 1 plus 1 over 0 minus 1 over 0 if I go to infinity or negative infinity, and that doesn't really make a lot of sense. However, that's why when I'm doing limits, sometimes I find the common denominator so that I can use some of those rules from pre-cal. Are y'all with me? But also you could have said this, if I'm really taking a limit to infinity, like if I look at this function and I say, what's the limit to infinity? And I plug an infinity in here, what are these values, what do they become? I plug an infinity there and an infinity there. What's 1 over a massive number? 0. So I really end up with 1 plus 0 plus minus 0, which is just 1. So the horizontal asymptote, you could have found it by thinking a limit to infinity or negative infinity, which is really where we need to be. When AP asks you a question like that, like how do you determine horizontal asymptotes? Your response should be even if you have a trick from pre-cal like we used, your response ought to be somewhere in the neighborhood of, oh, I'm checking a limit to infinity and negative infinity, because that's going to tell me what the y value is way out there. All right, so that gave me this. And then to find intervals where the graph is increasing or decreasing, what did we learn last week? The graph is always going to continue to increase in between what? Or always decrease in between what things? Critical numbers. So it's all about critical numbers. Now, it's possible that something's not a critical number, but it's undefined there. Because if you remember, and guys, these are the definitions you have to know. To have a critical number, what did we say a critical number was? And I'm going to continue to review these, guys. If I say something and you don't hear it, you really at this point ought to be writing it down and say, okay, I need to know the definition of this. What's the definition of a critical number? So where the derivative is 0 or doesn't exist, but it would also have to be defined. So what we say is a number in the domain of f, so it has to exist, right? So a number in the domain of f where the derivative equals 0 or d and e. Okay, so if I'm going to determine where the graph increases and decreases, I need to know where the derivative equals 0 or d and e. So I would probably rather take the derivative of this simplified version than the derivative of each of these, but you may not. The derivative, because I already had that, and I could do low d high minus high over low squared, but if you had taken the derivative of this, you'd have gotten something like 0 minus 1 over x squared, probably plus 1 over x to the 4th, and then you could have added it together at that point. But I chose to take the derivative of this rewritten function, low d high minus high d low over low squared. I distributed that. I distributed the negative 2x in, canceled whatever canceled, And then I even factored an x out and canceled it out and got to here. Are you with me? But if you had done low d high minus high, actually it wouldn't have been 1 over x to the fourth, it would have been like something x over x to the fourth. But if you had taken the derivative of this part right here and done it a different way, check it out. If I would take the derivative here, instead of this rewritten, I would have gotten this. 0, and then I would have gotten low d high, which is gone, minus high d low over low squared. And then I would have come over here and gone low d high, which is gone, minus high d low over low squared. And then when I find a common denominator there, check it out. If this x and that x to the fourth, I could cancel one of those x's. And then a common denominator would mean I need another x up here and another x there. And I would have gotten negative x plus 2 over x cubed, the same thing I have right there. So actually, honestly, it might have been easier just to take the derivative of that part. You with me? And then once I get to here with the derivative, I say, what are my critical numbers? And you need to write this stuff. The critical numbers are when the derivative equals 0. That's when that equals 0. So I set that equal to 0 and got 2. Or the derivative doesn't exist. So I set that equals 0 and got 0. But why don't I count 0 as a critical number? There's a VA there, right? Which we found out over here. Or you could say, wait, I can't plug a 0 in there. There's no value of 0. Are you with me? So always throw those out. Even if though they seem like critical numbers, I can only count the 2. And then, so all I did was mark the 2 on the number line. But remember in the video from Friday, I said if you ever do know where something's undefined, go ahead and mark that, especially the DNEs, like the vertical asymptotes. Mark that, because even though it's not an actual critical number, and you'll never have a max or a min there, you won't. But it still might change from increasing to decreasing there. So I checked the point on this side. Remember how we checked those for the number? This is called a number line analysis, if you forgot. I'm going to plug -1 into my derivative function, and that gave me a positive over a negative, which is negative. And then I checked the +1 in my derivative and got positive over positive, which is positive. And then I checked the 3 in my derivative and got negative over positive, which is negative. Right? So since I got a negative derivative value there, it's decreasing. Positive derivative value there, it's increasing. Negative derivative value there, not it. The function is decreasing. And then what did I learn about my first derivative test? So if your head's spinning right now and you're like, what's the first derivative test? The first derivative test said what? Anybody remember?
If it goes from negative to positive.
Can't use it, right?
If the function goes from a negative slope to a positive slope, then, or if the derivative goes from negative to positive, then it's a minimum, and if the derivative goes from positive to negative, it's a max.
Did y'all hear that? I would say that's almost perfect. The only thing, and I think she meant it, instead of saying min or max, you would say relative min or relative max. Because it's just, it may very well may be a max, but we know it's a relative max, right? Because we haven't checked anything else. But if you really look at this thing actually goes up forever and down forever. So it doesn't have actually a min and a max, but it does have a relative what? Max. So I would say this thing is increasing from 0 to 2. That was part B. Decreasing, and by the way, I just said it also. I would say F increases from 0 to 2. F decreases from negative infinity to 0 and from 2 to infinity. Okay? And then because, and this is all AP wants to see. AP is going to ask you questions like, what's the relative min? And because of the first derivative test, that she just quoted, the first derivative test says what? Because the derivative goes from plus to minus, there's a relative max there. Now if you look at this and go, but wait, the derivative goes from negative to positive. Why isn't there a relative min there?
Doesn't exist.
Because, yeah, there doesn't exist. There's no point there, right? So remember, all Fermat's theorem, which we haven't talked a ton about, but there's a mention of it in your notes. Fermat's basically says, hey, if you're gonna have a max or a min, it's gonna occur at a critical number. So that's not a critical number, so I can't have a relative min there, which makes sense, right? There's nothing there. All right, and actually, if you graph this thing, it ends up doing this, just following the asymptote straight down. So definitely increasing and decreasing on the function there, and then the relative max exists at 2, but to find the relative max, what do you have to do? Find the y value of the function by plugging it back in. So I'm going to plug 2 back into this function, and I get 1 plus a half minus a fourth, which is 5/4. And AP is going to turn around and go, justify your answer. And you're going to go, but this number line analysis says, and they're going to go, we don't look at number line analysis. Tell me why there's a relative max there. And you're basically going to repeat just what you said, which is the derivative goes from plus to minus there. That's all you need to say. And you can write it that cheaply. You don't have to say the derivative has a positive value on the left and a negative value on the right. F prime goes from plus to minus there. All right? Y'all with me? If you understand this right now, you're in a great place. If you're rusty on this right now, all the points where you are rusty, you really need to be able to communicate the questions back to me, the questions that I'm asking. And that's where you need to be on your test. Are you with me? And I know this is a lot. You're probably not going to have like a test with 3 problems or something. I'm going to try to find a way to ask you all these questions independently, so one mistake up here doesn't snowball on you. I really think I do a pretty good job of that. But you probably will have one. I'm not going to start you out like that. I would probably start you out like this, just to make it less confusing. And I'm probably not going to ask you a lot about HAs and VAs, although I think that's important to recognize there is one there, because that affects you here, doesn't it? A lot of people will look at something like this and go, oh, relative min there. Nope, it goes down forever there at that asymptote. Y'all seen this? All right. So if you feel pretty good about this, I think you're in a good place right now. There's some things that we didn't talk about. We didn't talk about the extreme value theorem. What does the extreme value theorem tell you? Been a couple days, right? The extreme value theorem says you are guaranteed to have a what? Max or min if what? You're going to have a max or min if it's continuous on a closed interval. And actually, that's it. If it's continuous on a closed interval, you will have a max or min. Is this continuous on a closed interval? I didn't even give you a closed interval, did I? So that doesn't hold here. Yes?
Well, any of this was in the non-mix test?
Expect it to be, but I will go back and check. If you ask me at the end of class, I'll run back through it and look, because normally I have that test on 2 days and then I have the 9 weeks right after. But because the 9 weeks ends, I wanted to make sure I could get the 9 weeks in, because that you can use it as a drop. And I figured you'd probably appreciate having a 9 weeks test with a potential drop than no 9 weeks test at all. So, but I'm pretty sure it might include some of it, but I'll double check. It may not. I might have just given you a mulligan on it. I don't know. I don't remember off the top of my head. Okay, new stuff. So I'm on page maybe 115? 117? Okay. So notes day 4. And my page numbers, mine says 121 because I've added some more junk in there, and I printed those a couple months ago. So here we go. Day 4, checking concavity and the second derivative test. Now right now you probably don't even know what concavity is. I have actually mentioned it a couple times in passing. But do you know how a function increases? It could be doing something like this, right? And that's increasing. It could be doing something like this, and that's increasing. It could be doing something like this, and that's increasing, right? Well, and I can check that increasing by checking the derivative. So if I check a derivative and I find that the derivative is positive, it increases, increases, increases. Well, there's another check I can make to find out whether it's not if it's increasing, but what kind of concavity it has. This is considered concave up. Concave up would be like if you kept extending it, it would make like a cup. So we say it's concave up like a cup. This would be concavity that is downward or concave down. If you keep extending it, it's concave down like a frown. And this is concave down a little bit, and then it switches to concave up a little bit. Well, concavity is a function of the second derivative. And you might remember on your test, you had one problem where you took the derivative again, and you end up with something like 24x squared minus 24x or something like that. You might or might not remember. That's going to talk to us about concavity. And where it switches, concavity isn't a critical number necessarily, could be. It is what we call an inflection point. So like say right somewhere right in here, where this graph switched from concave down to concave up, that is an inflection point. And we find inflection points, or at the very minimum, possible inflection points, the same way we find critical numbers. So when we were finding critical numbers, we were looking for places where the first derivative was defined, but what? Where the first derivative, or the function was defined, but the first derivative was either 0 or d and e. And those are possible, those are critical numbers that stood for possible relative maxes and mins. They may or may not be. We'd have to check, right? Sometimes you check and it goes increasing, increasing. Well, that's not a relative max or min. Sometimes it goes decreasing, decreasing. And that wasn't a relative max or min. But sometimes the function, you saw that it was increasing, decreasing, right? So those critical numbers were possible relative max and mins. Well, we're going to do the same thing with this time, but with the second derivative. And when we find a second derivative, those are places that we call inflection points. Possible inflection points. And they are places where the graph might change inflection, but it might not. So let's take a look at this rule, and see what we're going to do with it. So it's important that you understand, like I was just sketching, that if the graph is ever what we call cut kind of upward, we call that concave up. This is concave down. We don't say concave and convex like we might in physics. We just say the concavity is up or the concavity is down. I'm going to label this like CCU if it's concave up, or CCD if it's concave down, but you're welcome to put CU, CD. This is just the way I learned it, and it's kind of in my brain that way, but I have seen other calculus teachers just call it CU or CD. And you can see this one's both, right? Concave down on part of this, and then it switched and became concave up. And like critical numbers, if you find two critical numbers, can the graph be increasing and decreasing in between two? Or does it have to be just all increasing or just all decreasing? Between two critical numbers. Can it do increasing and decreasing? No. Well, with the exception of maybe like a VA or something like that in there, but in between two of those critical numbers, it's got to be all increasing or all decreasing. Well, in between two possible inflection points, it would have to be all concave down or all concave up. If it switches, then there would be another inflection point at where it's switching. Okay? Now, how do we find this? Well, concavity. First, I want to talk about that. You can check concavity by checking two things. And I'm going to put these together in a chart for you in a second. The first thing you can do, and I'm going to jump, it's actually the second thing I've written, but the first thing you can do is check the second derivative. If your second derivative is positive, okay, if the second derivative has a positive value, then you know that the original function is concave up. Lock that in your brain. If the second derivative is positive, the original function is concave up. See, now you know two things that describe the function. You already know if the first derivative is positive, hear this question, if the first derivative is positive, what does that tell you about the function? First derivative positive. Increase it, because that's positive slopes. Now you know if the second derivative is positive, concave up. Okay? First derivative negative, function is decreasing. Second derivative is negative, function's concave down. Okay? You with me? Now, In addition to that, there is a link that links the function and the second derivative. And this is going to start hurting your brain a little bit, maybe, maybe not. If the derivative is increasing, now think about that for a second. What does that mean, the derivative is increasing? Doesn't that kind of suggest that the slopes are increasing, right? The slope of f is increasing. Now you tell me, does this sound like slopes of f are increasing? This would be slope of 0, right? So you got a slope of 0, then a slope of a fourth, then a slope of a half, then a slope of 1, then a slope of 2, then a slope of 3. Are those increasing slopes? Does that make sense? How about this? Slope of -3, -2, -1, 0, 1, 2, 3. Does that seem like the slopes were actually getting bigger? They were increasing? What is that forming? Concave up. When the derivative of f, or the slopes of f increase, the second derivative is positive. And we know that when second derivative is positive, the original function is concave up. You now have a link between the first derivative, the second derivative, the original function, the first derivative, and the second derivative. And then the converse of whatever is true for f. If f is concave down, so if you look at the function, the f function, and it's concave down, then you know that the second derivative must have been negative there. But you also know what? The slopes of this were decreasing. Think about it. Slopes right here. 1, or let's just say 2, 1, 1/2, 0, -1/2, -1, -2. Didn't they start going down in value? And they made a concave down. These three things are linked, and it is massively important that you get it. And I'm going to give you a little cheat that you can write at the top of your page. I started doing this about 3 years ago, and since I've done it, the test scores on this have jumped at least a letter grade apiece. Check it out. And if you write this at the top, it's a great way to memorize this and to have it in your brain even when it's not in your brain, so to speak. Okay, so I'm going to give you the most obvious thing I could probably give you, and that is this. If f, I'm going to do it right here in this little box. If f is increasing, what does that tell you about the first derivative? If a function is increasing, what does that tell you about the slopes there? Does everybody see that? If a function increases, the derivative or the slopes are positive. So, function increases, the derivative of the function, which is the slopes, are positive. Easy enough? And if that's true, skip a space, come right here. What does it mean if the function's decreasing? Then the slopes are what? Negative. You're already more than halfway there. Now, if that's an equation, in algebra, can't you do the same thing to both sides? Like add 3 to both sides? This is an equation, right? These are equivalent. I mean, it's a kind of a weird equation that there's an inequality there, but these are equivalent statements. Well, if that's equivalent, I can take the derivative of both sides. And if I take the derivative of both sides, that tells you that the derivative increasing would mean what? The second derivative is positive. Or, if you know this, if the derivative is decreasing, the second derivative is negative. And you're almost there. And then what did we just say? If the second derivative is positive, what do you know about the function? It's what? It's concave up. So if the second derivative is positive, come over here, the original function's concave up. And if the second derivative is negative, come over here, the original function's concave down. And if you write that at the top of your test, right when you get it, and at the top of any problem that starts talking about relationship between f and f prime and f double prime, it's going to be like taking candy from a baby. I'm not kidding. It really is. I used to ask all these questions, and you have to stop and be like, okay, wait a minute. Let me think about what's going on. No, you don't have to think. Just look up here. Because this immediately gives you a relationship between f and f double prime, f prime and f double prime, f and f prime. See, now you got tons of information. If I ask you something about f, you now have a link to f prime in two places. F prime. And you have a link to f double prime, actually 4 places, right? Here to there, here to there. And you have a link to f double prime from the function in these 2 places. Are you seeing this? And you're going to see why this is important very shortly over the next week and a half or so. Maybe even longer, 2.5 weeks actually. So right here, I could look at this graph and go, hey, what is happening to the function? I could look at it and say, oh, it's concave up. All right? So I immediately know, even without calculating the derivative, if I look at this graph, I go, okay, I know that the second derivative, whatever it is, would have had a positive value here. But I also know that what's happening to the slopes here? -1, 0, +1. The derivatives were increasing in value as I moved across there. But I already know that too, because if the function's concave up, the derivative would be increasing in value. But I've got that link there, and it all starts with a very simple concept. If f is increasing, the derivative is positive. Take the derivative of both sides. That means concave up. Boom, you've got your statement for all your increasing and positive and concave up. It's the same statement for decreasing and negative and concave down. And I think I have that chart a few times moving forward. Okay? So make sure, it is a big deal, guys. If you start using the word it and you go, oh, it's positive, I'm going to go, it's positive. What's positive? The function's positive? If a function's positive, what does that mean? If f is positive, what does that mean to you? What does f mean? Hello? Talk to me, people. What does f mean? When you've been seeing functions, f of x equals blah, what does the f mean? The y values? So if I say f is positive, what does that mean? The y values are positive? What does that mean to you in a graph? It must be... No, not necessarily. Just above the x-axis though, right? F positive means it's somewhere above the x-axis. Now, what if I say f prime is increasing? What does that... what if I say f prime is positive? What does that mean? What's increasing? The f is increasing. So if I told you that f was positive, which I didn't even mention up here, that just means it's above the x-axis. If I told you f is above the x-axis. If I tell you f prime is positive, that means the function has what? F prime is positive? That means it has increasing values. F is increasing. If I tell you f double prime is positive, what does that mean? It means either the slope is increasing or the function is concave up. It's a link of all these. I know this is a lot to throw at you. That's why this stuff is used all year long. It's a lot, but if you get that part down, and I would have that little table, be able to memorize it, and for the love of all that is good, do not memorize it incorrectly, because then you're going to keep reusing that incorrectly all through your test. Sadly, that doesn't happen. Fortunately, it doesn't happen a lot. And here's your chart at the bottom of your page. Okay? So that's the same thing that we just said, stretched out in a big chart without equal signs, just arrows. But literally, if you can just regurgitate that on your test, and then you'll see how many times you'll answer questions. And then bottom line, here's our concavity test. We've already basically said it a million times. If you look at the second derivative, and you check a number on the second derivative, right? If you happen to see that some second derivative value is positive, then you immediately know that that function must have been concave up in that region. That's all you're learning. And if the second derivative is negative, like if you just randomly pick a point like we did on our number line analysis, you plug it in there and you get a negative second derivative value, then you know, oh, it must have been somewhat concave down in that area. That's all this second derivative is taking. And this is not the second derivative test. Okay, there's a separate thing we haven't even gotten to yet called the second derivative test. And it's basically the same as the first derivative test. It's used for finding relative maxes and mins. We haven't gotten to that yet. But this is a check for concavity. We don't call it the second derivative test. This is a concavity check. If you ever check a value, and you're going to do this the same way you check for increasing and decreasing. You're going to make a little number line, and you're going to check values. And if you get negative values for the second derivative, you're going to go like this and go, oh, it must be curved downward. Just like if you got negative values for the first derivative, you went decreasing. It's a separate little check that we're going to use to really help sketch out this graph nicely. All right? Now, remember critical numbers? What did we use critical numbers for? To see if there were relative maxes and mins there. Were there always? No. Sometimes it did this. Flattened out and then went up. Sometimes it went vertical and like this. But those weren't relative maxes or mins. But they were still critical numbers because the point existed, right? But we have to check on either side to see if the derivative went from positive to negative, or see if the derivative went from negative to positive. That's the first derivative test. Well, look, instead of critical numbers, we call these with the second derivative inflection points. Now we're going to look first for possible inflection points. Possible inflection points are graphs where the place it is defined, there's a point on the curve, but the second derivative is 0 d/e. But I don't know if they're going to be real inflection points until I check them any more than I know if critical numbers are going to be relative maxes and mins. So critical numbers, you might want to write this down. Critical numbers are what I use to find relative max and mins. Well, possible inflection points are what I use to find inflection points. But it's very easy to mess up your definition of, or not answer the question correctly. And I ask you, what are the inflection points? And you accidentally give me the possible inflection points. It's just like a critical number. You don't know if a critical number is going to be a relative max and min until you check. And I don't know if a possible inflection point is going to be an inflection point until I check. But it's the same kind of thinking. They're matched like this. All right? So be careful. If an inflection point, this is your if it's an inflection point, okay? This is definitely true. All right? Definitely it's going to be, the second derivative is going to be 0 d/e. But in order for this to be an inflection point, what does it say? You have to have a what? A change in your concavity. Just like you have to go from increasing to decreasing to have a relative max, you would have to go from concave up to concave down on your function to have an actual inflection point. And we're going to check those. You'll see right here, this almost the same way we did increasing and decreasing. So let's just look at a problem. It says determine the points of inflection and discuss the concavity. Now I gotta be honest with you. Most of the time on a test, I would be wanting to sketch this graph. So I would be doing a whole lot more than just finding concavity. I would be checking where the critical numbers were, where it's increasing, where it's decreasing, where it's constant maybe, where the vertical asymptotes are. And then when I did all of that, then I would get to this concavity. But this one's saying just check concavity, okay, and inflection points. So how do I find possible inflection points? Not where the first derivative is 0 d/e, but where the second derivative. So I'm going to take the first derivative of this function, which gives me 4x cubed minus 12x squared. That gets me to there. And then I'm going to take the second derivative of the function, which gives me 12x squared minus 24x. And I'm going to find out where the second derivative is 0 or where the second derivative is d/e. But I don't have to worry about it here because there's no denominator for me to worry about. All right? So where is that equal to 0? I factor out 12x, 0 and 2. Are 0 and 2 both in the domain up here? Yeah, it's a polynomial, right? Everything is in the domain. So those are called critical numbers, right? Those are called, we'll go with that. Those are called critical numbers, right? No, they're called inflection points, right? No, they're called what? Possible inflection points. So again, just like critical numbers are possible relative maxes and mins, possible inflection points lead you to inflection points, but you still have to check. So we're going to check just like before. But instead of checking where the derivative was positive or negative, we're going to check where the second derivative is positive or negative, and we're going to sketch what the function looks like. I probably should have put F right there. So, and the graph can only change inflection at what? Possible inflection points. Just like the graph can only change from increasing to decreasing or vice versa at critical numbers. Is this coming together? All right, so let's check my inflection points. My possible inflection points were at 0 and 2. So I'm going to check the second derivative at -1. Come up here, here's the second derivative. I like plugging it into the factor part, it's so much easier. Plug a -1 in there, I get negative times the negative is a positive. So what do I know when the second derivative is positive? The function is concave up. Right? Don't make it increase in there, concave up. And then I check the second derivative between 0 and 2. I checked it at 1. That gives me positive times negative. Second derivative is negative. What does that tell me about the function? Concave down. And then I pick a point bigger than 2, like 3. I check the second derivative there, and I get 36 times 1. But the real thing is positive times positive. So I know it's positive. The second derivative is positive. And what does that mean? The original function is concave up. So, if you have a possible inflection point and the graph changes inflection, what do we call the point where these two connect? Inflection points. So what were positive inflection points, now you know, you've checked them, because I changed inflection, I changed from concave up to concave down, or vice versa. That tells you wherever these things connect, and if you're looking at these and going, they don't connect, well, they would if they did that. I'm just sketching this, right? An idea of what's there. Where they connect, that would be your inflection point. Now, how do you find a point? You go back and plug it in. So I got to plug 0 back in my original function, and I get 0, so that inflection point would be 0, 0. And how do I find this point where these things connect? That inflection point would be what? 2, 16 minus 32 to negative 16. Y'all with me? So unlike a max or a min or a relative max or min, it's not a y value there, it's a point. So it's important that you get that. When you're talking about critical numbers, what are you talking about? I know this is not like scintillating information, but what are you talking about? X values. When I'm talking about relative maxes and mins, what are you talking about? Y values. When you're talking about inflection points, you're talking about points. Hence the name, point. All right? Y'all with me? So critical numbers are X values, and they lead to maxes and mins, which are Y's, and then inflection points are just points. And sometimes AP will say, hey, at what X values do the inflection points occur? Well, if that's the case, just say, oh, it's 0 and 2. Or what are your X values of your inflection points? 0 and 2. But the actual points are points. And that's different from critical numbers and maxes and mins, which are just X's or just Y's. And they could have made that less confusing. Instead of calling them critical numbers, they should have said possible maxes and mins, or possible locations of maxes and mins, and then they would have been similar to this, possible locations of inflection points. But they want to be fancy, I guess, I don't know. You tracking with me? And if somebody ever asks you, hey, justify your answer, you can't go, no, look, right here, look at this wonderful chart. You can see that the inflection changes, the concavity changes, so it must be, they're not going to look at this. So if I say justify your answer, why do you know there's an inflection point at 0, 0 and at 2, negative 16? Why do you know? Because the second derivative of f changes signs. And you could totally say, because the second derivative changes from plus to minus or from minus to plus, you could say that, but I would just say, why are these both inflection points? Because the second derivative of f double prime, changed from concave up to concave down or concave, I would probably just say changes signs. And then I can knock them out in both one fell swoop. Fair enough? Okay, so let's look at, and again, nice little table right here. Oh, and if you want to go back and talk about increasing and decreasing, what would I have to do? Oh, and if I ask you for intervals, is that what I asked you for in this? Oh, discuss the concavity. So if I wanted to discuss the concavity, I go and look at that chart and I say, oh, I know that this graph is concave up from negative infinity to 0 and from 2 to infinity, right? Concave up on those two intervals because the second derivative of f was positive there. And I know that this function is concave down from 0 to 2. I know it's concave down from 0 to 2 because the second derivative is negative here. And you've discussed the concavity, and you found out where the inflection points occur. And if you were graphing that, that's a lot of information. I mean, think about this. I can look at this now, just with concavity, and go, all right, 0, 0, 2, negative 16. It's if you look at the original function is positive x to the fourth. What do you know a positive x to the fourth graph does? Up to the right, and if it's x to the fourth, even, it's also up to the left. And so you know right now that this thing goes up to the right and up to the left, but it's concave what here? Concave up. And then what is it from 0 to 2? Concave down from 0 to 2. And then the rest of the way it's what? Concave up. I bet it looks something like that. Concave down, concave up, concave down, concave up. And if you used your other information like, hey, where are my roots? Right here, couldn't I have done the roots here? The x-intercepts? What are the x-intercepts here? 0 and, so maybe this thing, actually maybe it gets back a lot quicker. 0 and 4. And if you had done the first derivative test to find relative mins, I bet you find there's a relative min right there. Are you tracking with me on some of this stuff you could do? And you can also find where the graph was increasing or decreasing. You would have found that it decreased all the way to there and then increased the rest this way. When you start doing a full analysis of all this stuff, you really start seeing what it all looks like. And you can actually, and I know you're like, wow, I can do something that my calculator can do in 2 seconds. But we can break this stuff down manually now and answer really, really decent questions just through studying calculus and how stuff behaves. And people take this to the next level. I was talking to a woman who teaches calculus at Auburn yesterday, and we were talking about her son's taking calculus, and she's talking about, oh yeah, calculus is so great when it comes to doing derivatives in the financial market or analytics, because you're always examining growth behaviors and whether it's profit curves or loss, minimizing loss curves. You're looking at where these graphs have relative mins and relative maxes, and trying to adjust your behavior to fit that model and achieve more success or less loss. And calculus shows up all the time, and it's not overly difficult. It really isn't, but it requires a working knowledge of behaviors like this. Anyway, let's check out example, second derivative test. Yeah?
I don't understand from the chart, if it's increasing, but
What's
it's
it?
still, if the function is increasing, but it's still concave down, curving up like that. From the chart, it looks like if it's increasing, it's always going to be concave up.
If the function increases, it could increase this way,
Right.
or it could increase that way.
That's how, the second
Sorry.
way is what I'm confused about.
Like, what about it?
It's increasing, but it's concave down.
Yeah.
So, on the chart, I just don't
The
understand.
derivative increasing?
Just,
It's about this chart?
mhm.
Yeah, it is totally positive to have an increasing function. Totally positive. I mean, totally positive to be a function increase and have a positive concavity. That's a link there. But you could totally have a increasing and a negative concavity as well. Increasing function, positive concavity, increasing function, negative concavity. Like a parabola would be in. Do what now? The function is concave down. Did I do something wrong here? Oh, I changed my chart up. Normally I go from here, this is in a different order than I wrote it. Normally I write f increasing, and I write that, and then I take the derivative of both, and I get f prime increasing second derivative. This is in a different order than I originally wrote it up there. Sorry about that. But this is, right here, would you agree that f is increasing? All right, and you would also agree that f is concave up. And then right here, you could say f is also increasing, right? But this time f is concave down.
So you would have gotten a positive first derivative and a negative second derivative?
So here, yes, so here you would have a positive first derivative, because you can see your slopes on all of these were positive. Actually, no, on both of these, this is still a positive first derivative. Slopes are still positive.
But the second one, you would have gotten a negative second derivative.
Yes. right here, concave down, the second derivative is definitely negative, whereas this, the second derivative is definitely positive. I don't know why I have it written like this. I don't need to be changing orders up on you because that can be confusing. I don't think I did that again. This slipped my mind, maybe. Trying to see if I put that in there anymore. Sorry about that. I think a better way to think about it is the way I wrote it. Not like this, but saying, okay, this is pretty common sense to most people. Take the derivative of both sides, that gives you this. And then do the decreasing. If I have a decreasing situation, take the derivative of both of those, you get to here. And then go back and say, well, what does it mean about the second derivative being positive and negative? Original function is concave up, concave down. But to just give you an example, like y equals x squared. From 0, increasing, concave up, right? Graph like y equals square root of x, increasing but concave down. And I know when you see it curving like that, you might think, oh, does it eventually go down? Depends on if there's another critical. I mean, it's going to continue to do this. The only way it's ever going to decrease is if there was a critical number up there. Because it can't go from increasing to decreasing except at a critical number. According to Fermat saying it's going to have a max, relative max, it have to be a critical number there. So and you see these just keep climbing really slowly, but they do keep climbing. All right, now second derivative test. For some reason, no matter how many times I'm going to say this, what I'm going to say, people get in their head that a second derivative test is a test for concavity. Because they're like, oh, the second derivative is all about concavity. No, there are two tests for relative maxes and mins. One of them, in my opinion, is the one you should use whenever you have an opportunity. And you've already learned that. It's the first derivative test. And Carly said it in the back. She said, what does the first derivative test tell you? She said, if a function has a positive slope and then a negative slope, you have a what? A relative max there, assuming it was a critical number. Or if the derivative has a negative, if the derivative is negative and then positive, what does that tell you? The original function has a relative min there, right? Well, the second derivative test is another test to see if you have relative maxes and mins. It is not a test for concavity. The test for concavity is the test for concavity. All right? We use the second derivative to test for concavity. That's what I call checking for concavity. This is not the second derivative test. The second derivative test is a much less used, and some people go, why are you teaching it? Because AP will find a way to screw you with it if you don't know it. Okay? So I'm going to show you the second derivative test using, where am I? I'm going to show you what the second derivative test says, but it's so much more tricky to use it. I mean, it's not hard to use it, but it's so much more effort to use it because you actually have to find the second derivative. And as you're going to find soon enough, sometimes when you take the first derivative, you use the quotient rule. What do you end up with? Well, a big mess. Do you want to take the derivative of that mess? Probably not. You got to clean it up, simplify it. Hopefully it gets nice and clean. May not. What if you use the product rule? First to second plus second to first. And then I go, take the derivative again. It's a mess. So I'm not going to be able to get to it. So tomorrow, actually, you know what I'm going to do? I'm going to add a 5-minute little extra video to this. And you might want to just check it. I'll just put both up, but the second one won't get there for a while.
You sure you can look and see if the exam has any
Yes, I will do that as well. Hold on.